Hey, I'm Yakov, and in this video I present you the complete guide to protocols, in Swift and beyond. It starts with a high-level overview of the concept of software protocols, or interfaces, how they work and what problems they solve. To show you the bigger picture, I also demonstrate an alternative approach to software design, one which solves similar problems but doesn't rely on protocols. And after that, you get a deep dive into protocols in Swift. From the basics of how you declare and use them, to Interop with Objective-C, to advanced features like generics, associated types, and protocols method dispatch. Use the chapters below this video to quickly jump between its sections, and feel free to leave any questions in the comments. If you found this protocol guide helpful, I'd appreciate you giving it a thumbs up and subscribing to the Codebird. With that said, let's get started with the basics of protocols. If you've been developing software for more than a couple days, then you've definitely heard about protocols. But can you explain quickly and clearly why they exist and how they work? Do we even need protocols in the first place? In the previous episodes, I already had a look at memory management, Swift's type system, and automated testing. Now's the time to explore a new topic, and it is protocols, or interfaces as they're called in some other languages. Just like memory management, protocols are a big and important aspect of software development. Before we get into the weeds of protocols, I think it's a good idea to look at the big picture. What problem do protocols solve? Are they even necessary? And can we use something we already have instead? These are entirely valid questions. I'll start with a real-world illustration. Imagine you're living in the late 19th century, and there's this little thing everybody's talking about. It's called electricity. And from what you've seen and heard, this electricity thing does wonders. You being a talented engineer, just a software engineer, you naturally want to join what promises to be a true revolution. By that point, you already have a few inventions you're ready to offer to the public. But there's a problem. As we're still in the early days of electricity, it turns out that not everybody agrees how it should work. In result, cities across the country have different kinds of that electricity. Some use AC while others DC. Frequency and voltage also vary between places. And even the physical plugs don't always fill the sockets. The nation needs a single interface which offers universal compatibility in terms of voltage, frequency, and even physical design. Luckily, you're not the only one who realizes that. And so, welcome the standard power outlet. This outlet has certain physical properties, a specific size, shape, and pin configuration. These properties are set by your country. Also, your country's electrical code dictates what kind of electricity can flow through wires. If you're a device manufacturer, you just have to ensure that your products adhere to the same standards and have compatible physical plugs. And if you're a consumer, you can buy those devices knowing that they will work for sure. So now the problem is truly solved. All thanks to a single standardized interface. In this illustration, there's a single party which sets the standard and many parties who must comply with it. In software, it's exactly like that. Really, there's not much else to protocols, aside from naming maybe. Setting the standard is called declaring a protocol, and complying with it is called conforming to the protocol in some cases and using it in others. Protocols eliminate the need for software components to know about each other's internals, and even existence. All they have to know about is the common protocol definition. Like, one component wants to use certain voltage and frequency, and it counts that another component will conform to the expectations and supply them. This creates countless opportunities for engineers like you, because existing software now can be extended in the ways that their original authors couldn't even imagine. I like the electricity analogy. That's because it mimics not only the general idea behind protocols, but also many of its specific principles. For instance, while the government sets the standard, it doesn't actually generate electricity for you. Maybe it doesn't even know how electricity is generated. The government simply makes sure that everyone knows what to expect when they use the grid, on either side of the outlet. And just like that, the protocol author doesn't have to do anything beyond declaring the protocol. But everyone else depends on that protocol from now on. Another principle and another similarity. The protocol must be implemented in full. If you charge customers for electricity but don't actually supply it, one day you'll be accused of fraud. Swift, just as many other programming languages, is even more vigilant. The compiler simply won't build your code unless it can verify that your components conform to the protocol and implement its requirements. One important thing to know is that you can make your objects conform to a protocol partially. It's either all or nothing. But well-designed protocols don't force you to implement more than you really need to. And later in this video, I'll explain what counts as a good protocol. But wait, this analogy goes even deeper. If you do fulfill your responsibilities to generate electricity, that doesn't mean you always follow the standard. Maybe once in a while you supply too much voltage. Someone's phone or laptop may get toast, but the customers will have a hard time proving it was your fault. Unfortunately, here the compiler can't do much either. Your software components may conform to a protocol on paper, but not do what's actually expected of them. Well, if these parallels weren't enough for you, here's more. Electrical standards and software interfaces have a few other things in common. Namely, both ensure decoupling, abstraction, and interoperability. Let's have a closer look. Okay, decoupling. The government dictates the standard. The provider supplies electricity, and you use it for your needs. Everyone knows their own part, but not much else. You don't care how exactly electricity is generated. The provider doesn't care what devices you plug in and how they work. And the government doesn't care about any of you. And just like that, protocols allow different software components to interact with each other. But those components don't have to know about their internal workings. This limits everyone's concern and responsibility. Abstraction. In this case, it kinda extends the decoupling principle, to a point where you not only don't care how electricity is generated, but you also can find it out even if you wanted to. That's because all the complexities are hidden behind the simple interface of a power outlet. Likewise, the provider can come into your home and see what kind of devices you use. In software, implementation details are also hidden behind the interface. We say they're abstracted away. This is deliberate, and it's important that you don't make any assumptions about how those implementations really work. Because if you do, mistakes will follow. You can trust me on that. Interoperability. This principle means that any object which uses or conforms to a protocol can be swapped for another one, and this will not destabilize the system at large. In many cases, other objects wouldn't even notice the change. That is, of course, if the protocol is implemented correctly. Thanks to interoperability that protocols provide, you can, for instance, replace an Objective-C implementation with one written in Swift. In the power grid analogy, an example of interoperability is when you unplug your phone to plug the computer into the same outlet, or when you switch the electricity provider. In both cases, a concrete component has changed, but the system in general still works. Hopefully, at this point you understand what purpose protocols serve and what important properties they have. However, my explanations might be too abstract without specific use cases. And that's why I suggest that we have a look at a real-world scenario. In this scenario, solving a task without protocols would be really tough, if not entirely impossible. In iOS apps, just as in many software products, various lists, collections, and tables are the bread and butter of every developer. And in most cases, these structures are populated dynamically. That means you don't know what goes into each row at the time of development. Luckily, frameworks such as UIKit and SwiftUI take care of most tasks when you work with lists. I'll focus on UIKit because it still dominates the landscape. And I'd say that by this point, UIKit has pretty much nailed the whole process, so rendering, scrolling, and celery use are handled for you automatically. But there's one very important task which the frameworks can't solve without your help. In fact, without your help in this task, every other optimization and automation becomes useless. This task is actually supplying and presenting your data in the list. No matter how smart UIKit is, it doesn't know which data you want to display in each row, and how it should be laid out on the screen. That is why when you add a UITableView to your app, it asks you to provide a data source object. When the table view is displayed, it will consult the data source about how many rows there is and what goes into each of them. Well, guess what? UITableView data source is a protocol. The table view doesn't care what object will conform to this protocol and how it will be implemented. As long as this object returns the required data, the table view is fine with whatever. And again, it's your job to make sure the protocol is implemented correctly, because the table view relies on it entirely. For instance, if you tell the table view it should have 10 rows, but provide data for only 5, your app will crash. And the table view is not the one to blame. The final topic for today is what counts as a good protocol. If you've been paying attention when I explained the properties and principles of protocols, then you probably have a fairly good idea of what an ideal protocol looks like. But let's get down to the specifics, and also review a few concrete examples. First of all, a good protocol is clear and unambiguous. When you look at it, you know exactly what it does and why it exists in the first place. Perhaps you even have an idea of how you would implement it. Second, a good protocol should be complete and efficient. When it's conformed to by some component, it achieves all of its goals, but doesn't do anything extra, or what we'd call redundant. Third, a good protocol is robust when it comes to edge cases, unexpected input, or malicious actions. Of course, the protocol is merely an abstraction. The actual handling of all those unforeseen events is the job of the implementation. But still, the protocol's design influences a lot. And finally, a good protocol should be flexible and extensible. Ideally, you design it once, and then it can handle all sorts of situations, even those you don't imagine at the time of development. As you can see, clarity and completeness can sometimes conflict with each other, and so can robustness and extensibility. Designing a good protocol is not a simple task. I've seen not that many protocols that were good in every aspect, and I doubt many of my protocols were perfect either. But as you'll soon see, a protocol which violates one or more of these principles can still gain widespread use. So, to give you an idea, here's two examples of high-level protocols. One is really good, the other is notoriously bad. But both are used by billions of people every day. In fact, you're using them right now to watch this very video. The good protocol is HTTP, the one which powers the web as we know it. It's by no means a short or simple protocol. But conciseness wasn't among the required principles. HTTP is very clear in its purpose and mechanism. This protocol describes a way to exchange and present information using a set of well-defined methods, such as GET or POST. It is complete because it covers various aspects of communication, from simple text retrieval to complex data transfer scenarios. HTTP acknowledges potential failures. It provides a mechanism for error handling using status codes. It also supports caching and security mechanisms such as TLS. All that makes this protocol robust. And finally, HTTP is extensible. It evolved through several versions which added new features. But importantly, it maintained backward compatibility. And now let's have a look at a bad protocol. So bad in fact, that it has a track record of breaking the internet on multiple occasions. This is BGP, or Border Gateway Protocol. And it describes how data travels across the internet. BGP is a fairly complicated thing, with certain edge cases described ambiguously or in a language that's really hard to understand. At the same time, BGP doesn't forgive mistakes, and multiple outages were the result of misconfiguration. What's worse is that BGP lacks the security mechanism which could prevent bad actors from abusing it. The most common thing is route hijacking, and literally any AS operator can do this. And BGP isn't very extensible either. While some improvements have been implemented over time, it's not easy to roll them out everywhere. That's because there's about 1 million implementations, and all of them need to interact somehow. Protocols are a really powerful tool in software design. It gives developers the freedom to introduce, update, refactor, or replace individual components, all that without risking to destabilize the system at large. But protocols aren't the only way to achieve that degree of flexibility. Other mechanisms exist as well, and in some cases they turn out to be a much better choice. Subclassing is one of such alternatives, and in this video I'll cover what it is and compare the two approaches: composition and inheritance. Inheritance is a crucial concept in object-oriented programming, and I think that understanding its strengths and weaknesses is key to understanding protocols. Protocols aren't just another tool in your developer toolkit. They're actually the backbone of an entire software design paradigm. It is called composition. Let's start with that and then move on to inheritance. When you design a software system, you can choose from many approaches. For instance, you can build highly specialized structures for each individual use case. Or you can create jack-of-all-trades which can handle pretty much anything. Or you can do something else entirely. Composition in software design focuses on smaller, reusable components. You then mix and match them to get the result you want. They're like Lego bricks. You can follow the instructions and have the thing that's shown on the box. Or you can build something totally different using the same set of bricks. Composition encourages you to make those bricks small and independent from each other. Because of that, you don't risk repeating the same work over and over again. And because you're free to use only the ones you need, the resulting structure doesn't do more than it really should. Composition in software design comes down to has-a or can-do relationships. For instance, an airplane has wings and an engine, and it can move. But if you don't need an airplane, you can build other objects from the same set of traits. Like, a bird has wings and can move, but it doesn't have an engine. And a car can move and has an engine, but not wings. This approach offers greater flexibility, and it makes your code more modular. Protocols play a key role in enabling this paradigm. Different software components can work together, but at the same time they remain independent and loosely coupled. For example, the features that I mentioned, wings, an engine, and an ability to move, they can be defined as separate protocols, and different objects will conform only to those they really need. This approach is really powerful because it allows you to extend or replace components without the risk of breaking the whole system. And as you know from the previous video, this is exactly what protocols exist for. But if composition is so practical and protocols so powerful, why would anyone want to use something else? Long story short, protocols are not a one-size-fits-all solution. In some scenarios, they can introduce unneeded complexity. It arises from protocols' key feature. They define shared traits, but they don't actually implement them. When you need multiple objects which are similar in their behavior but not entirely the same, you'll need to manually implement that behavior multiple times. We call these tightly coupled systems. Of course, you can build some sort of helper object which encapsulates the shared behavior, but that will only increase the overall complexity. Just like nearly every tool in software development, protocols have not only benefits but also downsides. And instead of trying to adapt protocols for use cases they weren't designed for, we should consider some alternatives. Inheritance is one of them. If you're familiar with object-oriented programming, then you probably know that inheritance is one of its foundational principles. It offers an entirely different approach to sharing properties and behaviors. Unlike composition, inheritance focuses on objects' essence and not their capabilities. In other words, it's not about what an object has or can do, but what it actually is. Let's have another look at my previous example with a bird, a car, and an airplane. In the inheritance paradigm, what's important is that a car and an airplane are vehicles. Since all vehicles can move, the car and airplane simply inherit this behavior from their ancestor. While birds can move too, it's not relevant in this case. That's because birds and vehicles are unrelated, so any common traits they might have, they are received independently. This sounds pretty intuitive, because unlike vehicles, birds weren't created by humans. Most likely. Relationships of inheritance are mainly expressed using subclassing. When you declare an object as a subclass of some other object, it receives all of its properties and methods. The subclass can declare new ones or override existing, but that wouldn't detach it from its superclass. Moreover, any future changes in the superclass will be received by all of its subclasses automatically. The subclass, which is also known as derived class or child class, it continues to exist as a continuation of the superclass, also known as base class or parent class. In other words, the subclass is and always will be its own superclass, plus maybe something else. For instance, we might say that an airplane is a special type of vehicle. Just like all vehicles, it can move, but it does so by flying above the ground. So in addition to just being a vehicle, it also has wings. Maybe you noticed that in the last two illustrations I didn't mention yet another trait, the presence of an engine. That's because adding these little details suddenly makes these relationships much more complicated. And spoiler alert, this happens very often when you deal with inheritance. Like, is it fair to say that having an engine is a property of every vehicle? If so, the car and the airplane would simply inherit this trait. But as it turns out, we can't say that. For instance, gliders are vehicles because they can move, but they don't have an engine. If you want to get around this, you might come up with a different classification. For example, you might declare engine-powered vehicle as a subclass of the regular vehicle. In that case, the car and airplane could finally inherit the engine. But where would you then put the glider class? Since it doesn't have an engine, it can only inherit from vehicle. But this hierarchy means that gliders and airplanes aren't related that much. They both can move, but I would argue that they have more in common. Both have wings and both can fly. So this classification doesn't really work either. Perhaps the biggest advantage of using inheritance is that it makes your code highly reusable. If you're happy with the way some behavior is implemented in the base class, then you don't have to do anything. All your subclasses are getting their implementation for free. Code reusability is a great thing because it minimizes duplication. You don't have to manually copy any future changes from the base class to its derived classes. And thanks to that, you don't risk forgetting to do so. Another feature of inheritance also comes from object-oriented programming. It is called polymorphism. In short, a subclass is treated as an instance of its superclass. And that happens not only on the abstract level, like a car is a type of vehicle, but also in very much practical terms. For the compiler, every derived class is also the base class. So when you need to pass an instance of the base class, you can provide the derived class instead. The term for this is substitutability. It lies in the foundation of the Liskov substitution principle, or LSP. Here's how it's used in practice. UIKit offers you many UI elements, labels, buttons, sliders, and so on. All these classes are derived from UIView. Not always directly from it, but that's not the point. The point is, UIView declares a few methods for actually drawing the view. And that's all that's important when you want to display some element on the screen. This is why the addSubView method accepts instances of UIView itself or any of its subclasses. The method doesn't care if you give it a button, a label, or something else. To the method, they all are just UIViews. That's because this method only uses the behavior declared in the UIView class. Even though a button is really different from a label, UIKit doesn't need separate methods for them. And that is the result of polymorphism. One more benefit of inheritance is a high degree of extensibility. You can add new behaviors by subclassing existing objects. You don't need to modify the base class directly, and because of that, you can break the base class itself or any of its other subclasses. This is a key difference from composition. In composition, all traits of an object must be defined at the time of its own declaration. This difference allows developers to make design decisions later in the process, and that fact limits their potential impact. But inheritance is not all good. In fact, its drawbacks seriously limit the scope of its application. And one of the biggest side effects of using or abusing inheritance is tight coupling. When you make a change in the base class, it can ripple throughout the entire hierarchy. Derived classes don't have a choice whether to accept the change or not. And as a result, the system becomes more fragile. To avoid this, you have to be really careful when you design the hierarchy in the first place and when you make any changes later. The cost of a mistake is very high. Essentially, you'll have to rethink the entire classification, as you've seen in my illustration with gliders. Another issue with inheritance is that its emphasis on is-a relationships limits its flexibility. Basically, inheritance is appropriate for only a small subset of real-world scenarios. For example, the relationship crows or birds is a sound use case. Whenever you're asked for a bird, you can provide an instance of a crow. On the other hand, using inheritance to express the relationship birds are dinosaurs may be a little too far-fetched. Even though it's true, birds are dinosaurs. The problem is that they are so distant from each other, it makes little practical sense to actually treat birds as dinosaurs. One more problem with inheritance is that often its unsuitability becomes apparent only when it's too late. It's pretty easy to start using inheritance in your system, only to later realize that this was a mistake. Even in my example with just a few classes, it turned out that the classification I'd chosen wasn't entirely correct. Managing something more complex would be many times harder. Even understanding deep hierarchies of classes results in a lot of overhead. And one thing I learned about software engineering is that everything that's hard to understand makes mistakes nearly inevitable. Finally, there's the single inheritance principle, and it can make inheritance not a good choice in a lot of cases. Many programming languages, including Swift, don't allow multiple inheritance. It's when a class derives from more than one superclass. This restriction is mainly added to avoid the ambiguity of the diamond problem. Here's how it works. Two sibling classes are derived from the base class, and both override the same method. Then another class inherits from both of them, but doesn't override that method. How can the language know which implementation it should use? There's a few strategies, but all have some flaws. Because of that, Swift and other languages simply disallow multiple inheritance. In practice, you must decide from the start which base class your object will inherit from, and changing your mind later is rarely an option. Now compare this to protocols. Because they don't contain the actual implementation, nothing stops you from declaring the same method in two different protocols. Your object can conform to both of them, and the compiler will ask you to implement the overlapping requirement only once. Lastly, let's talk about how you choose the approach, composition or inheritance. The truth is, this decision is nearly always based on your specific use case. I can offer you a few guidelines, but keep in mind that they cannot cover all possible scenarios. From my own experience, when you're actually given a choice, which isn't always the case, it is safer to consider protocols first. That's because they're suitable for a broader range of situations. And besides, they're more forgiving to mistakes in your software design. Sometimes, however, you don't have a choice. In UIKit or AppKit, you're often required to subclass UIViewController and a subject or something like that. Inheritance has a limited number of use cases. It could be a good option when there's a clear is-a relationship between objects, and when you need the base class's functionality as is, maybe with just a few slight changes. Substitutability might be easier to achieve with subclasses, but I'd say that shouldn't be a defining factor. Every other scenario makes inheritance much less appealing. For instance, when you need greater flexibility, or when you need a more modular design, or when the components don't belong to the same hierarchy, or when you really want to avoid tight coupling. In all these cases, composition is pretty much your only option, at least it's the one you won't regret. But there's a good news. Composition and inheritance aren't mutually exclusive. You can actually mix and match them as you please. Here's just one possible example. And yes, it's also about birds. Everything on this channel is about birds. So, we need to design a software system. In this system, there's two bird species and two skills, flying and singing. The skills are declared as protocols, because let's say they're used in a different module. One more thing. For the sake of simplicity, I'll assume that all birds can fly. My apologies to penguins, chickens, and ostriches. So, I'll declare the bird class. Since we agreed that all birds can fly, this class will conform to the flying protocol directly. From now on, any subclass of bird will get the implementation of flight automatically. Now I'll declare the types for concrete bird species, crow and robin. They both inherit from the bird base class, and because of that, they already can fly without any further action. Between the two birds, only robins can sing. At least I wouldn't call crow sound singing. So only one of the derived classes conforms to the singing protocol. And here's the result. Both birds can fly. And if I declare another one, it will receive this behavior right away. But only one bird can sing, and if I try to call this sing method on a crow instance, the compiler simply won't let me. This design has allowed me to implement the system without duplicating a single thing. No protocol conformance and no method had to be declared more than once. In terms of efficiency, it couldn't have been better. So this has been inheritance in a nutshell. It's a powerful tool which lets you reuse your code efficiently. But just like all powerful tools, this one is also a double-edged sword. Inheritance is appropriate only for some relationships between objects, so using it everywhere isn't something I would recommend. In many ways, protocols are similar to other objects you can create in your project, structures, classes, actors, and so on. The key difference is that you don't provide any implementations in protocols, only signatures of methods and properties. Actually, there are some useful exceptions to that, but I'll get back to them in the next video on protocols. Protocols can declare pretty much every kind of member a Swift object can have. That includes properties, methods, initializers, and so on. Moreover, a protocol can for instance require that its property is mutable, or that its method is asynchronous. To declare a protocol, you start with the protocol keyword, followed by the name. When you list a property as a protocol requirement, you have to mark it as either mutable or immutable. You use the get and set keywords for that. But keep in mind that if you don't include the set keyword, it doesn't mean that the conforming object must use a constant. It simply says that when this property is used through the protocol, it can only be read, but not written to. However, anyone who has direct access to the implementation can still change the value. When it comes to methods, you define them in the protocol like normal functions, only without curly braces. You only include the signature, but not the body. The method's parameters and return type are declared just as usual, and so are other details such as static, mutating, async, and throws. There's one important distinction between properties and methods. With properties, you can declare less but implement more. The protocol can require only read access, but the implementation can still be mutable. With methods, however, it is the other way around. For instance, if the protocol doesn't say that the method is asynchronous, then your implementation can't be async either. But you can declare more and implement less. A throwing method in the protocol can be implemented as a non-throwing, and an asynchronous requirement can be implemented by a synchronous method. Let's put all of this into practice. Here I have the bird protocol, and I'll go over some of my design decisions. First of all, each bird has a name, and the name is declared as an immutable property. That is why protocol users don't have write access. The protocol also has two methods. Both are declared as async, and the fly method also has the throws keyword, because newly hatched birds can fly. In most cases, it's a good thing that any type can conform to any protocol. But in some situations, you actually want to limit that to only reference types, such as classes. That comes in handy when you need to make sure that your objects use reference semantics. For situations like this, you can restrict the scope of your protocol. You do that by putting this anyObject constraint after a colon. That's what I'm going to do with my protocol, because the bird instance should be passed by reference. If you have no idea what I'm talking about, I can refer you to this video. With these tools and options, your protocols can be flexible and powerful, but without requiring too much of you at the time of implementation. So now let's talk about how you conform your objects to protocols, and how you implement their requirements. In the base case, any Swift type can conform to any protocol. That includes structures, classes, actors, and even enumerations. You can also make a built-in type conform to a protocol. That's because protocol conformance can be declared in an extension to that type. That means you don't need to modify its original declaration. If you want to modify it, you can of course. But actually, declaring protocol conformances in extensions is a good practice. This way you can clearly see which properties and methods come from the protocol. Of course, there are exceptions. For instance, you can declare stored properties in type extensions. In the simplest case, I've got a protocol with only one method, and a structure that needs to conform to the protocol. Everything is really easy, so instead let's have a look at something more interesting. For instance, if I try to conform the same structure to the bird protocol, the compiler won't let me. That's because I explicitly restricted its scope to reference types. So instead, I'll use a class. It already has the name property, so when I declare a protocol conformance, it will satisfy one of its requirements automatically. And it's totally fine that the protocol expects a constant while I've got a variable here. But the methods from the protocol don't exist in the class yet. In a previous video, I mentioned that protocols must be implemented in full, so my project won't build until I add the missing methods. Luckily, the compiler can figure out what's missing and add stops for me. However, before I try to build the code, I'd like to make some changes. Let's say I'm building a robotic bird. Such birds waste no time sleeping. In fact, they're always watching. The bird's battery can be swapped instantly, and because of that, making the sleep methods asynchronous is unnecessary. I can simply remove that keyword. Also, robobirds can fly from the moment they hatch, or get off the assembly line, so I don't need the throws keyword either. But watch what happens when I try to add something that wasn't in the protocol. The sleep method was declared as a non-throwing, and because of that, I can add the throws keyword in its implementation. That means if the bird's new battery fails, the sleep method can throw an error. Just as I mentioned, enumerations can also conform to protocols. Here's an example. Don't forget that Swift enums can have stored properties, and that sometimes limits your options. One thing you should be careful with is declaring protocol conformances for types you don't control. That applies to both built-in types and types which simply come from another module, like an open source package. Technically, nothing stops you from extending them like this. But also, nothing stops the original author from adding a symbol with the same name but different behavior. The compiler will mark your property or method as duplicate, but it won't highlight the calls to it. So in the best case scenario, you'll need to change every such line. And in the worst case, the behavior will change without you even noticing. That is to say, I don't recommend abusing this feature. Now that I've got a protocol and an object which conforms to it, I can finally start using its properties and methods. There are two ways you can work with protocols in Swift. You can use them as existential types or as generic constraints. This time I'll only show the first way because it's simpler, even though it's not always efficient. So, protocols as existential types essentially look and behave just like other objects, structures, classes, and everything else. You simply use the name of the protocol as the type of a property or function parameter. The any keyword is optional in situations like this. At this point, I can already access any property and call any method declared in the protocol. I can pass the protocol object as a function parameter or make it someone else's property. Keep in mind, however, that the protocol object's actual type is no longer visible to the compiler. From now on, I can only use the properties and methods declared in the protocol. So, for instance, if my class conforms to a protocol but also has some methods of its own, I won't be able to call them. That's part of the price you pay for the convenience of existential types. There are performance implications too, but I'll save them for another time. In my previous video, I explained inheritance as a paradigm that you can use instead of protocols. In that light, you might find surprising that protocols themselves support something that looks awfully like inheritance. It's not true inheritance, but it works in a similar way. One protocol can inherit all requirements from another protocol, and then add more requirements on top of that. Again, it's not true inheritance as with classes, and because of that, there's a few important differences. The key difference is the underlying mechanism. While a derived class points to its superclass, a derived protocol basically just copies all requirements of the super protocol. In terms of actual use, there are two more prominent differences. First, protocols do allow multiple inheritance. Because protocols don't provide implementations, you don't face the diamond problem that I explained in the previous video. And second, protocols can't override other protocols' requirements. But again, you'd never need that because there's nothing to override. A more appropriate name for protocol inheritance is protocol composition. But in my experience, both terms are equally common. When it comes to conforming to compound protocols, it's basically the same as fulfilling the requirements of all its parts. In fact, your object can just conform to each of them individually, without ever mentioning the compound protocol. The compiler will synthesize the overall conformance behind the scenes. As the final topic for today, let's talk about a technique called protocol-oriented programming. It's not an entirely new concept in software development, but Swift takes it to a whole new level. The idea is that you use protocols to describe software components in terms of behavior. Then you can combine these protocols to get an object which does exactly what you want, no more and no less. But the tools available in Swift make achieving these goals much easier. For instance, value types and their ability to conform to protocols. They generally make your code simpler and faster. Instead of creating a class, providing a separate initializer, and employing reference semantics, you can get the desired behavior from a structure, or even an enumeration. Protocol composition, or inheritance, lets you combine individual requirements and avoid the unneeded complexity. This approach results in cleaner and more maintainable code. And protocol composition in Swift is enhanced by protocol extensions. They allow developers to provide default implementations for properties and methods. This means that a conforming type gets the desired behavior for free, and the same behavior can be shared by all conforming types. This effectively solves the code duplication problem and minimizes the risk of errors. Protocols in Swift are really powerful. I'd say they're much more powerful than similar tools in other languages. And the main reason for that is not even the core functionality of Swift protocols, but all the extras you can find in the language. Because, to be honest, it's pretty hard to invent something radically different in this area. I'd say the most prominent of those extras is protocol extensions. At first glance, they might look similar to extensions for other types, structures, classes, and so on. But in the case of protocols, they play quite a different role. Protocols with extensions are something like two-in-ones, the protocol itself and its own implementation. Here's how it works. In the protocol declaration, you list all the requirements of your protocols, properties, methods, the usual stuff. But then you've got a chance to implement some of those requirements right away in a protocol extension. In their syntax, extensions are really similar to the normal way of conforming to protocols. And unlike protocols themselves, extensions do expect you to provide method bodies. As a result, when it comes to conforming concrete objects to that protocol, they won't have to implement its properties and methods explicitly. Instead, they'll just be using the default implementations. If you want, you can actually implement all of a protocol's requirements in its extension. If you do so, conforming an object to that protocol will take just one line of code. Here's how it can help you. Let's say that your software design requires a certain behavior from its components. But implementing this behavior is straightforward enough, so it can be shared between all such components. In this case, if you provide a default implementation, you'll need to write its code only once, but all conforming objects will be able to use it. Of course, the conforming objects can override default implementations with their own versions. It's done the same way you implement protocol requirements in the first place. And unlike overriding methods and classes, you don't even need special keywords for that. In my previous video on protocols, I explained the core concepts of the paradigm called protocol-oriented programming. Well, protocol extensions and default implementations are the tools that largely enable this paradigm. If you remember, one of the key principles of protocol-oriented programming comes down to building small, reusable, and composable components. Protocol's ability to bundle default implementations allows the components to be truly small. They don't have a bunch of redundant functions dragging behind each time you implement a protocol. And of course, sharing a single implementation across all conforming objects makes mistakes less likely. Providing default implementations is the most interesting capability of protocol extensions. But it's not the only one. Besides implementing protocol methods and properties, protocol extensions can function just like extensions of other types. In them, you can declare methods and computer properties, and they'll be available whenever you use the protocol. Just keep in mind two important things. First, if you declare something brand new in a protocol extension, this symbol will not become a protocol requirement. As a result, the conforming object won't have a chance to provide its own implementation. And second, there are performance implications of declaring symbols like that. You might be surprised, but the protocol requirements are actually slower and more complicated behind the scenes compared to protocol extensions. Of course, we're talking about a difference that's entirely negligible in most cases, but it's worth keeping in mind anyway. In the meantime, let's have a look at the different ways you can declare protocol requirements. In the previous episode, where I explained the basics of Swift protocols, I mentioned that you can declare pretty much every type of member: properties, methods, initializers, and so on. I showed a few examples of methods, including throwing and async functions. But I saved one more kind for later. I'm talking about generics. Protocols in Swift offer full support for generic methods. You declare them the usual way, with angle brackets. Inside those brackets, you put the generic types. You can also specify some constraints for those types if you need them. Just as in other generic contexts, the implementation must be able to take care of any supported type that you use. So for instance, if the generic type has no constraints, the caller can pass any parameter to the method. Then it's your implementation's responsibility to validate and handle all the possible values. Basically, generics in protocols look and behave just like they do in other objects. They allow individual methods to support more than one type as a parameter or return value. This ability makes your code more flexible, but without compromising its performance. And just like in other contexts, generics and protocols are resolved individually at the time of each function call. That means that different methods in a protocol don't know about one another's parameters. For instance, these two methods are supposed to work together, but technically they remain independent. Each of them supports the entire range of value types, and because of that, each has to validate and unwrap them individually. So, what can you do about that? What if you're building a system where different protocol methods do need that knowledge about each other's types? In that case, instead of generics, you can use associated types. Associated types in Swift are a tool that's exclusive to protocols. At first glance, they're similar to generics. The protocol declaration offers some sort of a placeholder, and when you use that protocol, you fill this placeholder with a concrete type. But if you dig a bit deeper, you'll discover that associated types are actually quite different from generics. First of all, they completely solve the problem with generics that I mentioned. When you declare an associated type, this single type is shared between all protocol requirements. As a result, different methods can rely on one concrete type. They don't have to employ defensive coding strategies such as typecasting, nil checking, and so on. But that's not the only benefit of associated types. Perhaps you know that generic methods are resolved statically when you call them. But associated types get resolved even earlier than that. When you implement the protocol, you have to specify the associated type explicitly. You can use a type alias for that. Or you can just replace the placeholder with your concrete type in method implementations. As a result, you know which values are fine and which aren't from the very beginning, even before you try to compile the code. And associated types aren't limited to being simple placeholders. They can constrain the types of objects accepted by the protocol. For instance, let's say you're declaring a protocol that's designed to merge two collections together. Obviously, merging two individual objects, like two numbers, it doesn't make a lot of sense. So in that case, you can restrict the associated type to only those objects which conform to the collection protocol. By the way, collection itself is another protocol with associated types. As a result, you can implement the protocol for two integer arrays, but you can't do the same for two integers. The compiler simply won't let you. Just to clarify, constraints like that work with generics too. The difference is that with generics, the restrictions are enforced when you call the function. But with associated types, you can even implement the protocol for your own type. This helps you to detect errors early in the process. Besides that, associated types provide a higher level of abstraction. What that means is they sort of fix type relationships in place and allow multiple protocol methods to work together. Once you've implemented a protocol in this manner, its associated type is already specialized. It can't be changed anymore. Associated types and protocols highlight one of Swift's core principles. The language strives to move as many tasks as it can from the runtime to the compile time. This helps you make your software more robust, because the earlier your unknowns become known, the easier it is to find and correct any mistakes. And when it's possible, Swift goes even further and tries to make the unknowns known even earlier, just as you type in the code. That's the deal with associated types. However, protocols with associated types are more difficult to use in practice. First of all, when it comes to implementing such protocols, only one concrete type can take the placeholder's place. That means if you want to merge collections with strings and collections with integers, you'll need to have two separate implementations. Again, you get in two highly specialized tools. But the challenges with associated types don't stop here. Using such protocols as existential types was entirely impossible in the past. And even now it comes with significant restrictions. Normal protocols and protocols with generic methods can be used like that pretty easily and with no limitations. But protocols with associated types take much more thought when you design the system as a whole. I'll show you what I mean later in this video. But before that, there's one more topic I want to discuss. As you can see, associated types make your protocols more flexible and reusable. They offer placeholders, and objects which conform to such protocols replace those placeholders with concrete types. Effectively, the conforming objects can decide for themselves what type they will support. But what if you want the conforming object itself to be a placeholder? I think it's easier to see with an illustration. Let's say I want to have a mechanism for duplicating objects. I can declare a duplicator protocol for that. But as you know from this video, duplicating objects isn't always a straightforward process. Because of all that, a universal duplicator implementation won't solve the problem entirely. Perhaps I'll need to have separate components for duplicating different types. One approach is to declare an associated type that represents the object being duplicated. This associated type will be used as both the parameter and return value of the duplicate method. With this protocol, I can implement individual duplicators for each type I want to make copies of. I can create duplicators for different structures, classes, enumerations, and so on. Each of them will know exactly how to make copies, because they know what type they're duplicating. But you probably see that this approach isn't very convenient. Whenever I want a copy of some object, I need to instantiate an entirely new component and pass the existing object to it. Ideally, each type should be able to produce a copy of itself. So, instead of using an external duplicator, I want the object itself to have a duplicate method. I want the object to conform to this new duplicable protocol. But how do I express the relationship between types now when I no longer have an associated type? This is where the self requirement comes into play. The self keyword is more or less equivalent to a normal associated type, except you can't really choose what concrete type it will stand for. That's because self refers specifically to the type of the conforming object. So, for instance, if my duplicable protocol is conformed to by a string, then the duplicate method will return a string. And if some class conforms to that protocol, then calling the method will produce a new instance of the same class. Protocols with the self requirement have the same restrictions as protocols with associated types. I'll demonstrate them later in this video. But before I do, let's briefly discuss how you make a choice. As you can see, associated types are really powerful and flexible. But with those power and flexibility come a few restrictions on how you can use such protocols. Because of that, using associated types makes sense when you need to clearly define type relationships between multiple protocol methods. For instance, let's say all methods of your protocol must work together on values of a single concrete type. In that case, you'll avoid a lot of boilerplate by using associated types. However, when your protocol methods don't really depend on one another, or when some of them don't even need abstraction at all, then associated types might be an overkill. In that case, generic methods will let you use simpler syntax, while still providing enough flexibility. But generics, associated types, and nearly every other tool that's available to you, they're just that, tools. In most situations, they can work in combination and complement each other. So even though it often seems like you have to make a choice, in reality you can mix and match different tools any way you need. And the following demo shows just that. So, for this practical exercise, let's say you want to build a component which multiplies an object by a number. What multiplication means specifically depends on the object itself. For instance, multiplying a number works just as you'd expect. And multiplying a string means repeating it a given number of times. For now, let's just focus on these two types, strings and integers. Without generics and without associated types, you'll have to declare two separate protocols. You'll also have to implement them separately, although it's worth noting that the same object can conform to both protocols. But this approach is neither flexible nor scalable. The protocols are incompatible with each other, and if you want to support another data type in the future, then you'll have to repeat every step manually. Let's see how we can improve this design. Using generics, you can declare a single protocol. Doing so gives you a nice and elegant interface, and you can use it with any data type. Problems begin when you try to implement the protocol. The generic parameter has to be checked and cast to a supported type at runtime. So far, nothing terrible, but that's because right now you can multiply only strings and integers. But if you add support for more types, this construction will grow even uglier. Okay, let's try to start over and solve this problem with associated types. Instead of a generic parameter, you can declare an associated type O for the object. Then you've got two components which conform to the protocol, and each of them deals with just its own concrete object type. If you add another type in the future, you'll need to implement the protocol once again. While it doesn't seem like a perfect situation, it's actually not that bad. That's because you still have only one protocol, and you don't have to change any existing code. But can we find something better? I'll present you my version a bit later, but before that, let's take a step back and have a look at how we use the protocols. The beauty of protocols is that to use them as another component's dependencies, you don't really need to have functional implementations. Imagine you've declared all the 4 protocols, but haven't implemented any of them. Now you're working on a new object, and it should call the multiplication methods. With the plain protocols, it's really easy. You just specify protocol names as the types of properties. After that, you can call the multiplication methods directly, as if they were defined on a structure or class. In other words, the protocols are used as existential types. This is possible even without having an implementation. That's because each of the protocols clearly tells the compiler what type it supports. In that case, the compiler can verify that you're not trying to give it something else. The downside of this approach is pretty obvious. Managing the different flavors of multipliers becomes the job of the client object, meaning the object which uses the protocol. If at some point you introduce another multiplier, you'll have to declare a new protocol, implement it in a new object, and then update the client. It's not very convenient, right? Using the protocol with generics is much easier. You declare a single property, and again you can call its multiply method directly on this property. What's even better is that you can call the same method with parameters of any type. While the plan is to support only strings and integers, resolving the parameter is the implementation's job. And for now, you don't have any implementations, so nothing to worry about. And again, the compiler has no problem with that. While it doesn't know our plans, it relies on the generic parameter to type check the code. This generic parameter has no restrictions, so the compiler assumes that the implementation can handle any value. And now let's see what we have with associated types. The first thing you'll notice is that you can't declare a property the same way as before. This time, you'll have to use the any keyword. This keyword was introduced in Suite 5.6, and it's actually meant to transform protocols into existential types. But in this case, it still won't help you. Let's see why this happens. In the previous 2 cases, I emphasized that even without the implementations, the compiler had everything it needed to type check the code. But now the protocol declaration alone is not enough. The compiler can't verify that the integer or string you're trying to pass is actually supported by the protocol. In a way, protocols with associated types remain incomplete until they're implemented, and until the associated type is specified explicitly. And that is why you can't use such protocols as existential types like that. To fix this, you need to resolve the ambiguity, and you've got more than one place to do so. One of them is the client object. You basically have to de-abstract the protocol by fixing its associated type in place. You declare a new protocol, and you use this where condition to tell the compiler that the associated type will always be an integer from now on. Then you repeat the same steps for strings. After that, you go back to the first option that I showed. As a result, you get to use the protocol as an existential type, but at the cost of having more code. Another way to resolve this situation would be to eliminate the use of associated types entirely. You can declare a new protocol with a generic method, and its implementation will use concrete types directly. I won't stop here for long, but here's the code. And as a final alternative, you can simply pass this ambiguity up the dependency chain. This involves using the protocol as a generic constraint, but I'll save this big topic for the next video. For now, I'll only say that while this approach doesn't look as nice as existential types, it offers huge performance benefits. But now let's go back to the question I asked. How can we improve the software design in the first place so we don't have to deal with problems later? I would move the multiplication to the actual object. For that, I'll declare the multiplicable protocol. This protocol is gonna have the self requirement. As for the multiplier, I'll declare it as a protocol with a generic method. But the generic parameter will have a constraint. Specifically, only types which conform to multiplicable can be passed to this method. Implementing this method takes a single line of code. Essentially, it delegates the multiplication to the object itself. And here's the result. I can multiply strings and integers, and when I want to add support for a new type, I just have to conform it to the multiplicable protocol. I need no changes in the protocol, its implementation, or the client component. The downside of this approach is that I'm extending built-in types. While I don't believe it can backfire in this scenario, this is still something to be aware of. This time I'll be using Swift protocols in Objective-C and vice versa. You might consider Objective-C outdated, but if you develop apps for any Apple platform, then the legacy of Objective-C still affects your work every day. So let's have a look at how protocols in Swift and Objective-C are similar, how they differ, and how you can combine them efficiently in your projects. Objective-C is a language with a pretty long history. It was created back in the 80s, and truth be told, it hasn't changed that much until this day. But the concept of protocols or interfaces, it has an even longer history in software development. So it shouldn't surprise you that Objective-C has a mechanism for the very same purpose. Protocols let you define shared traits and behaviors. When Swift was introduced over 10 years ago, its seamless compatibility with Objective-C was one of the key selling points. When it comes to protocols, Swift more or less delivers on that promise. In Swift, you can use Objective-C protocols without much extra effort. In many cases, they work as is. In fact, you can mix components written in Swift and Objective-C in pretty much any combination. For instance, you can take a protocol declared in Objective-C, implement it in Swift, and then use that implementation as a dependency of another Objective-C component. But you've probably guessed that it's not always that easy. If you've had a chance to work with both Objective-C and Swift, you definitely notice that they have a huge difference in their core paradigms. This difference affects protocols just as well. So while in basic tests, protocols in Swift and Objective-C can interoperate fairly well, you shouldn't ignore their distinctions. I invite you to have a closer look at them. For this video, I built a small demo project, and you can find it at the link below. This is a prototype of a word processing app. It lets you enter some text and say a couple details about it. In the first iteration, this app has a protocol declared in Objective-C, and I want to implement it in Swift. Then another Objective-C component will use this implementation to do its own job. I'll have a couple more tasks later, but for now let's focus on using Objective-C protocols in Swift environments. In a previous episode on protocols, I mentioned that Swift lets you use all sorts of objects to implement them. For instance, when you don't need reference semantics, your protocol can be conformed to by structures and even enumerations. In these cases, you often get better performance and safer concurrency. But in that regard, Swift is sort of an exception. Other programming languages typically reserve value types for primitive things, such as booleans or numbers. Objective-C is one of those languages. When you want to implement a protocol, you have to use classes. And because using Objective-C protocols employs the Objective-C runtime, Swift has no choice but to inherit the same restrictions. Basically, when a protocol comes from Objective-C, you can assume that it has the AnyObject constraint. And you can't change that even if you only use the protocol in Swift. That's the case with my demo project as well. Counting the number of characters in a string could easily be implemented in a structure, or even a static method in enumeration. But because the protocol comes from Objective-C, I have no choice but to use a class. And oftentimes, Objective-C protocols don't simply force you to implement their methods in classes, but actually they require you to use a particular base class. In a previous episode on protocols, I briefly explained the inheritance paradigm, and this paradigm is deeply ingrained in Objective-C. NSObject is the root class of nearly every object hierarchy, because it provides the interface to Objective-C's runtime system. Many protocols expect the conforming objects to have that interface too, and because of that, you're often required to inherit from NSObject. This could have a performance impact in older versions of Swift. That's because inheriting from NSObject used to enable message dispatch for the entire object. Fortunately, this has been fixed, so now other class members can continue using Swift static or dynamic dispatch. One thing you do need to keep in mind is using the Obj-C attribute with Swift code. This attribute makes the code visible to Objective-C, but it also makes the code slower, again because of message dispatch. Unless you really need that, I wouldn't recommend using this attribute. But in my demo project, I do need to expose the string manipulator implementation to Objective-C. That's because it is used as a dependency of word processor, another Objective-C object. Implementing the methods doesn't take much effort. But one thing you might notice is that the protocol has 3 methods, but the compiler requires only 2 in the implementation. My code compiles even without the third one. The number of words method is marked as optional, and optional methods in Objective-C are a pretty interesting topic. Perhaps you remember from this video that Swift lets you provide default implementations in protocol extensions. In practice, you might think of them as optional protocol requirements, because they're kind of optional to implement. But in reality, they're not optional. In Swift, every protocol requirement must have an implementation. If you don't provide one explicitly, then it must be present in a protocol extension. And if the compiler doesn't find any implementation, it simply won't build the code. On the other hand, Objective-C offers support for truly optional methods. When you declare a protocol, its symbols are treated as required by default. But protocol declarations can also have this optional section. Everything below it is optional to implement, and everything above is required. If you want to declare some required methods after optional, you can use this required marker anywhere in the protocol. Effectively, your declaration can have any number of required and optional blocks. And now let's consider the interesting way Objective-C understands the word required. The string manipulator protocol has 2 required methods and 1 optional. As you've seen a minute ago, Swift will happily build the code with only the required methods present. But with Objective-C objects, even required methods sort of become optional to implement. With default project settings, you'll only get a warning if you forget about some of protocol requirements. Otherwise, the project will compile and launch just fine. That's because in Objective-C, nearly everything happens at runtime, so a missing or incomplete protocol conformance technically doesn't prevent the compiler from building the code. This can be pretty confusing when you're used to working with Swift like I am. But luckily, you can change the rules with a single compiler setting. If you want to have a more familiar behavior in protocols, you can add this warning flag in build settings. Let's assume we've done just that, and now focus on optional methods. In my object, I've implemented the required methods but skipped the optional one. What do you think would happen when another Objective-C component calls it? Well, if you work with the language, you know that it has one answer to pretty much any problem. A runtime exception, in other words, a crash. Calls to optional methods which aren't implemented will compile just fine. But when these lines are executed at runtime, your app will crash. To avoid runtime exceptions, you have to manually check if the method is available at runtime. For that, you use the response-to-selector method. This method plays an important role in the Objective-C runtime, and that's why I had to inherit my class from NSObject. Of course, it's hard to call this solution elegant, but at least it's better than a crash. Let's assume that in another update, I replace this implementation with a Swift version. This won't solve every problem completely, because the objects still interact through the original Objective-C protocol. But despite that, Swift can make this code much nicer and safer. Swift treats optional protocol methods as optional closures, and you can use them just like any other optional object. If you want to call such a closure, you have to unwrap it. This can be done explicitly or inline. And that is why there's a question mark before the method's parentheses. Choosing the approach might seem like a no-brainer, right? Who'd want to use optional binding when a single question mark can fix everything? Well, almost everything. There's one really important distinction that often goes unnoticed. If you use inline unwrapping for a method that's not implemented, no code will be called at all. And sometimes this can get you in trouble. For instance, completion handlers are supposed to be called no matter the result. But when you unwrap optional methods inline, it's very easy to forget about the else branch. Only a few months ago, I found and fixed a bug just like that in the Firebase SDK. You probably know that Firebase has hundreds of contributors and many millions of users. But even in a project that large, the intricacies of Objective-C can be just too much to handle. So now, I can be pretty certain that even if the optional method is not implemented, the app will handle this scenario just fine. Earlier in this video, I said that Swift doesn't support truly optional protocol methods. It would be more accurate to say that Swift doesn't support truly optional methods in pure Swift protocols. But when a Swift protocol is exposed to Objective-C, the rules change. Let's talk about that. When you want to make a Swift object visible and usable in Objective-C, you mark it with the Obj-C attribute. But this only works with the data types and features which are supported by both languages. Protocols are sort of a mixed bag in that sense. Obviously, protocols in general exist in both Swift and Objective-C. But in previous videos, I repeatedly told you that protocols in Swift are much more capable than in other languages. That's why some of their features can be used in Objective-C, and you have to keep that in mind when you design the protocol in the first place. Generics are one of those features. Objective-C lacks support for generic types, so protocol requirements with generics can't be accessed from Objective-C. Of course, there are workarounds, such as type erasure, but it's hard to call them convenient. You'll most likely have to redesign the protocol without generics. Associated types are another feature of Swift protocols which you can't use in Objective-C. In the previous episode, I explained how associated types enable one protocol to handle many use case scenarios, without typecasting or type erasure. But this feature relies on Swift's type system, and Objective-C is not compatible with it. The same goes for self-requirements in protocols. Because they're related to associated types in most aspects, they have similar restrictions. In my demo project, I wouldn't need generics or associated types. All I want to do is declare a Swift protocol for word processor's delegate. This protocol should be adopted by the view controller, and this view controller is written in Objective-C. The delegate should handle just a couple types of events. The word processor will be telling it when processing starts and ends, and when there's an error in the processing of the input. In Swift, I would declare this protocol in an extension to word processor. But Objective-C doesn't support type nesting, so instead I'll have to declare it separately. Again, if this were a pure Swift protocol, it would probably have a single method which reports processing state. The state can be described within enumeration. But while Objective-C does support enums, they're much more limited than in Swift. So instead of a single method, I'll need to have 3 separate functions. The distinctions don't end here. Let's say the delegate is mostly interested in errors, so it should have a way to ignore other state changes. Swift protocols support default implementations for that. But unfortunately, you can't export them to Objective-C. In that case, you'll have to implement each and every method explicitly. But that is, unless you mark them with the optional keyword. You see, unlike pure Swift protocols, protocols exposed to Objective-C can have truly optional methods, with the same features and restrictions I explained earlier. Of course, now you'll have to unwrap the methods before calling them, but at least this solves the practical problem. At this point, the view controller can conform to the delegate protocol, but only implement the methods for reporting errors. While my demo project doesn't show every possible scenario you can encounter, it highlights the key aspects of using Swift and Objective-C protocols together. As a reminder, you can find the source code on GitHub. And from the starter branch, you can retrace my steps or do everything your way. In summary, protocols in pretty much any language have the same purpose, but they may offer somewhat different tools and mechanisms. I highlighted a few important aspects of using Objective-C protocols in Swift and Swift protocols in Objective-C. I'd say default implementations are a really important distinction. They play a crucial role in protocol-oriented programming. But since Objective-C doesn't support default implementations, it's not gonna be easy to export a complex protocol-based design from Swift to Objective-C. You'll most likely have to rethink the entire architecture, and that's rarely something you would enjoy. So if you suspect that your Swift code will need to support Objective-C at some point, you better keep these limitations in mind from the very beginning. When people talk about using protocols in Swift, they typically refer to this. Here, the protocol name appears as if it were a concrete structure or class. And you can use protocol names in pretty much any place where you can use a concrete structure or class. For example, you can declare an instance property, pass the object in a function parameter, call its properties and methods, and so on. But in a way, all this is just a smokescreen, or at least a huge simplification. In a strict sense, protocols don't really exist at runtime. They're basically a build time construct. The purpose of protocols in Swift is to enable compile time type checking and define a contract that the compiler can enforce. If the conforming type violates this contract, your code won't build. But that's not to say protocols don't have implications at runtime. They absolutely do. However, these implications are not as straightforward as they might seem. But first, one formality. When a protocol is used like this, it's called an existential type. The name basically means that you can use the protocol as if it existed at runtime, even though it doesn't. That's possible through a hidden mechanism in Swift, and this mechanism impacts the code's performance. To make the properties and methods of a protocol callable at runtime, behind the scenes Swift creates what's called the existential container. It is basically a black box that wraps around the implementing object. It exposes only the protocol requirements and forwards incoming calls to the implementation. The existential container acts like a proxy, similar to the site table that's created when you use weak references. And if you don't know what the site table is, I can dispatch you to this video. As you can imagine, proxying calls at runtime adds some overhead. The question is there a faster way to do all this? There is. Actually, there are two ways for achieving that. The first one is using the concrete type directly. When you declare a protocol conformance on a type, the compiler forces you to implement its requirements. But if you then use the conforming type itself, the runtime doesn't need to use the protocol in any shape or form. It just knows that the properties and methods exist on the actual type. While there are valid cases for this approach, it's not what we typically want to achieve by using protocols. Usually we want polymorphism. In other words, we want our code to not know about the concrete type that implements protocol requirements. And we want the ability to swap the implementations as we please. So the other way of achieving better performance with protocols is by using them as generic constraints. Generics are a big topic in itself, but the general idea is that you declare placeholders for concrete types. When you then build the code, the compiler scans it for the types you've actually used throughout the codebase, and it can produce concrete versions of the symbols. It doesn't always work like that, but you get the general idea. And here's where protocols come into play. When you declare a generic type, you can restrict it by using generic constraints. Doing so instructs the compiler to make sure that every concrete data structure you use in place of the generic type declares a conformance to that protocol. If it doesn't, the code won't build. But if it does, the compiler will be able to emit concrete versions of all the calls. It will effectively bake the implementation into the codebase itself. The protocol is just no longer needed. The calls can be sent straight to the implementation, and again, there's no need for proxying. At least, this is the best possible outcome. As I mentioned, generics are a big concept that deserves a separate video, and maybe more than one. Some of generics aspects can be predicted with full certainty. A single generic parameter can have multiple constraints. For example, this method requires its parameters to conform to both identifiable and hashable, which is a common prerequisite for diffable data sources. In fact, generic constraints aren't even limited to protocols alone. For instance, these two methods accept subclasses of NSView, but also require them to implement the methods of the embeddable element protocol. Actually, generic constraints are even more powerful than that. But to achieve all their power, you need to use a slightly different version of the syntax. The where keyword is an alternative way to declare generic constraints. But unlike the angle brackets, where constraints let you be more specific. When you declare the generic types constraints using the where keyword, you can also constrain its associated types. In that earlier video, I demoed associated types using the concept of an object multiplier. Now suppose you're working on a class that uses that object multiplier, but only for strings. Using a where constraint, you can design this class in a type-safe manner by ensuring that the multiplier's associated type can only be a string. You won't be able to use any other implementation of the protocol. Perhaps from this illustration you can see the limitations of using protocols as generic constraints. You can try and drill this genericness throughout the entire type hierarchy, but at every level this list of generic parameters will only grow longer. What's the answer to this? Type erasure. As the name suggests, type erasure removes the information about object types, making them more universal. But by doing so, it also erases the benefits of generics, at least to some extent. The mechanism itself is quite simple. In the full implementation, you basically create an alternative hierarchy of classes. They erase types at every level. In a shorter version, you erase some types but leave others. For example, here I've removed generics that refer to the business logic component, but I kept the generic parameter for the type of data this component can process. What isn't that simple is deciding when to employ type erasure. On one hand, you don't want this tail of generics to pierce through all your classes, because it would make them tightly coupled, and that is something we try to avoid. But on the other, you do want to get the performance benefits of using generics. The rule of thumb comes down to the scope, usage requirements, and performance expectations. If generics penetrate the class hierarchy too deeply, or if you need to store multiple implementations in a single collection, or if performance isn't absolutely critical, then it may be a good idea to terminate that generic tail. But when your types are well contained, and especially when you want to squeeze every single memory bit and processor cycle from the device, then generics are the right tool to use, even despite their syntactic bulkiness. The next topic relies heavily on your understanding of method dispatch in Swift. I had a detailed episode about it, so I won't repeat myself in this video. That is to say, if you need a refresher on method dispatch, I recommend you to pause this video and go watch the linked episode. In short, the term method dispatch refers to how the programming language links calls to functions with their actual implementations. To execute some instructions, the runtime needs to dispatch that call to the implementation. Swift supports multiple modes of method dispatch, and static or direct dispatch is the fastest of them. You may remember something about the existential container. Basically, when you use a protocol as an existential type, Swift creates this wrapper box that intercepts and proxies calls to the implementation object. But what is this container really, and how does it work? The existential container is a concrete data structure. Its job is to receive calls for protocol properties and methods and forward those calls to the correct implementation addresses in memory. The structure of this container fully explains why using protocols as existential types has negative consequences for runtime performance. The existential container has three key parts. First is the conforming value, or perhaps more often just a pointer to the object on the heap. Second is the value witness table. It's not very important right now, because it's basically just a set of functions that help manage the value, create, move, or destroy it. But third is the most crucial part. It's called the protocol witness table, and it contains the addresses of the properties and methods that satisfy protocol requirements. Here's how it all works together. When you use a protocol as an existential type, Swift will derive an existential container from it. When you then use a property or method, your call will be directed to this container. And to actually execute the requested behavior, the runtime needs to do three things. First, it looks up the address of the implemented symbol in the protocol witness table. Then it gets the value, which is the implementation object. And finally, it dispatches the actual call to the memory address while using the value as the hidden self-parameter. From this mechanism, one that has a separate structure for looking up methods at runtime, it is quite clear that using protocols as existential types involves dynamic dispatch. Just like classes vtables, protocol witness tables enable polymorphism, but at the cost of proxying every method call just as it happens. This indirection is the key reason why existential types have a performance impact at runtime. And for situations where you can't afford to pay that price, Swift offers an alternative way, using protocols as generic constraints. Let's see how they differ. I mentioned that when you use a protocol as a generic constraint, the compiler mostly uses it for type checking at compile time. In the best case scenario, it will then erase the protocol entirely, leaving only the calls to concrete objects that implement that protocol. This process is called monomorphization, or specialization. It's when the compiler sees polymorphic code and transforms it to separate specialized versions for each concrete type. Monomorphization results in more instructions embedded in the executable, but it's not a big deal compared to the two huge benefits it provides. First, everything happens behind the scenes. You never see this generated code and you don't have to maintain it. And second, everything happens at compile time. The system doesn't need to proxy and resolve any function calls at runtime, which is a huge performance booster. By baking the concrete types into the resulting IR and then machine code, the compiler can enable static dispatch, where method calls link directly to their implementations. This is the best outcome, but it is far from guaranteed. You see, Swift uses a hybrid approach for generics. It will decide whether to monomorphize them based on a few signals that it collects at compile time. For example, using implementations that have static dispatch, enabling whole module optimization, or making the function inlineable increase the chances of it getting replaced with a specialized version. But in many cases, you may just get polymorphic generics. They work through something called the generic box. This is the default mechanism for generics, and Swift falls back on it when it can guarantee a high degree of optimization. That is often the case when you use generics across module boundaries or when you optimize your codebase for its size. With polymorphic generics, the compiler will still emit generic functions, which means they'll be using dynamic dispatch at runtime. But there are two important distinctions from using protocols as existential types. First, even when generics aren't completely specialized, the protocol itself is still only used for type checking. When the code is compiled, the protocol's requirements become the methods of the generic type itself. In other words, the protocol effectively doesn't exist at runtime. And second, even though you haven't achieved real static dispatch, the generic box works faster than the full existential container. That's because the latter has a fixed size for the implementing object, and that size often requires the object to be stored on the heap and retrieved separately for each function call. In contrast, the generic box can store the value itself and pass it to the function directly. So far, I've only talked about the core protocol requirements, the properties and methods you declare in the protocol itself. These symbols are known as points of customization. But in addition to them, you know that you can also declare symbols in protocol extensions. And they are entirely different. Because these symbols are not part of the protocol declaration, they are not considered points of customization and they don't enable polymorphism. You can't implement those symbols in the conforming object. Instead, you must do so right in the protocol extension. And because there's no polymorphism, Swift can heavily optimize the execution of those instructions. That is why protocol extensions always use static dispatch. This is really good for runtime performance. But it also results in one tricky situation that can make the behavior of the code less intuitive. Let's have a look at this and a few other interesting scenarios. The tricky situation is this. You've got a protocol with one required method. This method has a default implementation in the protocol extension. The extension also declares another method that's not part of the protocol. Then, in the conforming object, you implement the protocol's required method, even though it's got a default implementation. But this object also declares a method whose signature matches the non-required method in the protocol extension. Finally, you instantiate the object and use it three different ways, as a concrete, existential, and generic type. The question is, what will be the result of calling each method? When you use the implementation directly, the compiler and runtime know nothing about the protocol. For that reason, they always use the methods declared on the object itself. For an existential type, the result is slightly less intuitive, though still fully expected. The runtime doesn't know much about the concrete type, besides that it exists and implements the protocol. When it encounters a call to the protocol requirement, which is a point of customization, it is designed to consult with the protocol witness table in the existential container. And the rule is that the concrete implementation always overrides the default one. Because of that, the runtime calls the methods from the actual class, not the protocol extension. But when it sees the method that's not a point of customization, it calls the version specified in the protocol extension. That's because the runtime has no knowledge of the concrete type. And here's the most surprising scenario. When you use the protocol as a generic constraint, the compiler does know about the concrete implementation, but the runtime doesn't. Since I'm using a struct, which guarantees static dispatch for the implementation and improves the chances of generic monomorphization, you might expect to have the implementation's methods called in both cases. But that's not what happens. Just like in the previous scenario, you get the required method from the struct, but the non-required method from the protocol. Confusing, right? This behavior can be explained though, at least to some degree. You can view the transformation as a two-stage process. First, even if the compiler fully specializes the generic placeholder, the generic type still receives its methods from the protocol. At that stage, the struct's non-required method is just ignored. The generic type now has two methods, and one of them is configured to use the protocol witness table and resolve the required method at runtime. But then, at the second stage, the compiler decides that the protocol requirement can be optimized even further. This time, it replaces the protocol witness table with a direct call to the implemented method, therefore achieving static dispatch. That's what happens here. While we can't guarantee the result of the second stage, we can say for sure that the non-required method from the conforming object will be ignored. Protocol extensions always use static dispatch, and because of that, the compiler doesn't even try to look for any alternative implementations. As you can see, the underlying mechanism of protocols in Swift is quite complex and isn't always fully predictable. But what we can do to achieve better performance involves providing the compiler enough signals to optimize as much as possible. The good news is that many of these principles aren't limited to protocols. They can be applied in most other situations. For example, using value types such as structs enables static dispatch by default. Also, generics, even if not fully specialized, they still work faster than type erasure through existential containers. But the key idea that I'm trying to convey in every video on this channel is that all these things are just means to an end, or tools. Yes, ideally you should master these tools, though not because they're valuable in themselves, but because they help you design the overall system in the most robust, efficient, and extensible way. And that is what gets you to the end. This has been the final part of my complete guide to protocols in Swift and beyond. I hope this video has given you enough information to use protocols with confidence and proficiency. If you found it helpful, give it a thumbs up. And if you have any questions, leave them in the comments. Subscribe to the Codebird for even more engineering content. I will see you in future episodes on this channel. Until then, make your protocols fly.